Welcome to session 8 of UGBS 301. In this session, we shall consider points and interval estimates. In the previous session, we looked at sampling and sampling distributions. Sampling statistics are values that are estimates of the population parameters, which are mostly unknown. This session is concerned with how best we can estimate population parameters using an interval instead of just a point. So, after completing this session, you should be able to distinguish between what a point estimate is and what a confidence interval estimate is. You should be able to construct and interpret a confidence interval estimate for a single population mean using both the Z and the T distribution. You should be able to determine the required sample size to estimate a single population mean with a specified margin of error, and then you should be able to form and interpret a confidence interval estimate for a single population proportion. Lastly, we will be able to determine the appropriate sample size for a research. Now, a point estimate is a single number, and in the previous sessions, we've looked at how we can use point estimates as representatives for our population parameters. Therefore, we learned that if you want to estimate the population mean, then we can use the sample mean as the best point estimate for the population mean. Also, the sample proportion P bar can also be used as the best point estimate for the population proportion. But in terms of interval estimates, we are saying that instead of just providing a point as the estimate for the population parameter, we want to provide an interval where the actual population parameter could be found in. And this interval, you would attach to it some level of confidence. For example, if I'm supposed to find the average age of all students within the University of Ghana campus, instead of saying that perhaps the average age is, say, 26 years based on my sample, I could say that I am 95% confident that my age or the actual average age would lie between, say, 23 years to 29 years. That is an interval with a level of confidence. And this is what we call confidence interval. So in a confidence interval, we are looking at how much uncertainty or how much certainty is associated with a point estimate of a population parameter. An interval estimate provides more information about a population characteristic more than a point estimate. And such interval is what we call the confidence intervals. So it takes into consideration the variation in sample statistics from sample to sample, and is also based on the observation from one sample, and it gives you an information about how close an unknown parameter is to the estimated parameter or the sample statistic. And of course, we state them in terms of level of confidence, and we are never 100% confident. We can be 95% confident, we can be 98, 99, and so on and so forth, but we cannot be 100% confident. The general formula, therefore, for all confidence interval is given as the point estimate plus what we call the critical value multiplied by the standard error. The point estimate plus or minus the critical value times the standard error. And the confidence level is given as the confidence in which the interval will contain the unknown population parameter. And this is always given in terms of percentages, and these percentages are always less than 100%. Suppose that we have a 95% confidence level. Then what it just means is that we can write it as 1 minus alpha equal to 0.95, and it also means that in the long run, 95% of all the confidence intervals that can be constructed would contain the unknown true parameter. Now, in constructing confidence intervals, there are certain things that we will need to consider. In the first case, we will be constructing intervals for the population mean. And we will first consider situations where sigma, or the population standard deviation, is known, or the population standard, and when the population standard deviation is unknown. We also have what we call a margin of error. If you go back to the relation for constructing the confidence interval, we said the confidence interval is the point estimate, which in this case is x bar for the population mean, plus or minus the critical value, which is given as z alpha over 2, multiplying the standard error. Now, the product of the z value, or the critical value, and the standard error is what we term as the margin of error. Therefore, the margin of error is the amount that is added and subtracted to the point estimate to form the confidence interval. There are some factors that affect the margin of error. For instance, if the data variation is large, then you realize that the margin of error would decrease as the level of variability decreases. Similarly, your margin of error would increase as your level of variability increases. Also, our margin of error will decrease as our sample size n would increase, and the margin of error would reduce if our level of confidence also reduces. So, it tells us that there are three main factors that affect our margin of error. First is the variability, second is the sample size, and third, we have the level of confidence. So, let's try and see how we would construct a confidence interval for our population mean, given that our population standard deviation is known. We take into consideration certain assumptions, and the first assumption is that the population standard deviation is known, the population is normally distributed, and if the population is not normal, we are going to use large samples. So, our confidence interval estimate is given as x bar plus or minus z alpha over 2 times our standard error. If you want to consider a 95% confidence interval, then we are saying that we have an area, or our lower confidence limit is negative 1.96, and our upper confidence limit is positive 1.96, and it tells us that 95% of the items or the intervals that will be constructed will be contained within this area. That is 1 minus alpha being equal to 0.95. Alpha is what we call level of significance, and alpha is divided into 2. Now, you realize that if I'm supposed to make alpha the subject here, you see that alpha will be equal to 0.05, and if you break alpha into 2, one part would have alpha over 2, which is 2.5%, that's 0.0025, and then the other part would also have another 2.5%, which is 0.025. Now, these are some commonly used confidence intervals, and then their critical values. If your confidence level is 80%, then it means that your 1 minus alpha is just like 0.8, and your z value is 1.28. If your confidence level is 90%, then your z value is 1.645. If your confidence level is 95%, then your alpha, 1 minus alpha, is 0.95, then your z alpha over 2 will give you 1.96. Similarly, if your confidence level is 99%, then your Z alpha over 2 is 2.57. We have other values that you can check. But in most cases, the most commonly used confidence intervals are the 90%, the 95%, and the 99% confidence intervals. So, 90% confidence interval, our Z alpha over 2 is 1.645 once again, 1.96 for a 95% confidence interval, and then 2.57 for a 99% confidence interval. We take an example. A sample of 11 circuits from a large normal population has a mean resistance of 2.2 ohms, and we know from past testing that the population standard deviation is 0.35 ohms. Determine a 95% confidence interval for the true mean resistance of the population. So, we have that our confidence interval is given as the sample mean plus or minus Z alpha over 2 times our standard error. We have our sample mean or our mean resistance being equal to 2.20, then we have plus or minus, and because we are drawing a 95% confidence interval, our Z alpha over 2 value is 1.96, then we have our standard error, which is 0.35 times the square root of 11. Now our margin of error, which is the product of these values, gives us 0.2068, which means that our lower bound for the confidence interval is going to be 2.2 minus 0.2086, which will give us 1.9932. Then our upper bound for the confidence interval will be 2.20 plus 0.2068. That gives us 2.4068. And therefore, our 95% confidence interval for the resistance would be 1.9932 and between 1.9932 and 2.4068. The correct interpretation for this is therefore that we are 95% confident that the true mean resistance lies between 1.9932 and then 2.4068 ohms. An incorrect interpretation is that we don't say that there's a 95% probability that this interval contains the true population mean, but we say that we are 95% confident that the true mean resistance lies between 1.9932 and then 2.4068 ohms. We now consider the second situation where our population standard deviation is unknown. We first considered a situation where our population standard deviation was known. We want to look at the situation where we don't know our population standard deviation. Therefore, if the population standard deviation is unknown, then we can replace it by using the sample standard deviation S. In other words, S comes to replace sigma. This introduces extra uncertainty since S is now variable from sample to sample. And hence, instead of using the normal distribution, we would use the T distribution. So our assumption is that in case our population standard deviation is unknown and our population is normally distributed, or even if our population is not normally distributed, we are going to use large samples. We are going to use the student T distribution. And the confidence interval for the estimate is such that X bar plus or minus T alpha over 2, we have S, which is the sample standard deviation, divided by the square root of n. The T distribution is a family of distributions, and it depends on what we call the degrees of freedom. The degrees of freedom will be calculated by the number of observations that are free, or is defined as the number of observations that are free to vary after the sample mean has been calculated and is defined as the sample size minus 1, which is n minus 1. This is just a specimen of our T table. You see that when you go down, you have the degrees of freedom, and when you go across, you have the values of the z, the alpha over 2. Therefore, assuming that our sample size is 3, then it means that our degree of freedom is n minus 1, that is 3 minus 1, which is 2. And if our alpha over 2 is, say, 0.05, then reading from this T table, we realize that our value will be 0.05 at the top and then 2 at the sides, corresponding to a value of 2.920. That means that our critical value is 2.920. We take an example. A random sample of size n equals to 25 has x equals to 50, and then that sample mean equals to 50, and then the standard deviation equals to 8. We are required to form a 95% confidence interval for mu, assuming that the population is normally distributed. So, we know that our confidence interval is given as x bar plus or minus t alpha over 2 times s divided by the square root of n. And we also know that we are going to use the t distribution because we don't have the population standard deviation being known. That is why we are replacing it with the sample standard deviation, which is s. That means that we are going to use our t distribution, and the degrees of freedom is n, which is the sample size, minus 1, which gives us 25 minus 1, which is 24. Therefore, our confidence interval is t alpha over 2, n minus 1 degrees of freedom. And since we are forming a confidence interval of 95%, we are going to have our alpha being equal to 0.05, and alpha over 2 therefore becomes 0.025 with a degree of freedom of 24. This gives us a t value, or a critical value, of 2.0639. Therefore, our confidence interval will give us 50 plus or minus 2.0639 times our standard error, which is s over square root of n. That gives us 8 over 2.5. And this gives us an upper bound of 53.302 and the lower bound of 46.698. When you have large samples and you have our population standard deviation being unknown, then you will see that our distribution, which is t distribution, would approach the z distribution, that is the normal distribution, as the sample size increases. Therefore, an approximation is sometimes used when we have n being greater than or equal to 30. Therefore, if our sample sizes are large and then our standard deviation for the population is unknown, we should have that our confidence interval be x bar plus or minus t alpha over 2 times s over root n. But then, if n is large, this can be approximated to x bar plus or minus z alpha over 2 times s over the square root of n. That is to say that our t distribution has been converted to a z distribution because of our large sample size. Given this information about confidence intervals, about margin of errors, and the things that we've learned so far, we can also determine the sample size or the correct sample size for our research. Therefore, when a researcher has a desired margin of error in mind, the challenge for him or her is to determine what sample size he must use in order to attain the desired margin of error. Now, given a confidence interval or a confidence level, the formula for determining the appropriate sample size is given as n equals to z alpha over 2 squared times sigma squared all over e squared, where e is our margin of error. This is attained on the condition that our population standard deviation is known. If you don't know it, we would estimate it using the sample standard deviation. Therefore, we will say that the factors that would affect your sample size for your research is actually 1, your confidence level, 2, the level of variability within your sample or population, and 3, the margin of error that you want to set for yourself. Let's take an example. If sigma is equal to 45, what sample size is needed to be 90% confident of being correct within a margin of 5? So given this information, we know that our population standard deviation is given as 45. Our confidence level is given to be 90%. Then our margin of error is given to be 5. So our n is equal to z alpha over 2 sigma over e all squared. We have that our z alpha over 2, our confidence level, our critical value or the value for our confidence level is 1.645. Our population standard deviation is 45. Then our margin of error is also given as 5. So we have 219.19 samples. Approximately, our required sample size is therefore n equals to 220 samples. And it is desirable that you always round up. Earlier, we said that when sigma is unknown, we select a sample and estimate sigma with the standard or with the sample standard deviation given as S. So, if unknown, sigma can also be estimated using the required sample size formula, as we already stated. Using this, we can estimate sigma using our sample standard deviation S, and use a value of sigma that is expected to be at least as large as the true sigma. So this presents to us a summary for what we've done so far in terms of this confidence interval estimation. If our population is normally distributed and our sample sizes are large, and given that our population standard deviation is known, then it means that our confidence interval is x bar plus or minus z times the standard error. If our population is normally distributed, our sample sizes are large, and our population standard deviation is unknown, then we are going to use either the t distribution or we would use the z distribution, given that the sample sizes are large. That is, z is used as an approximation of t. Similarly, if our sample size is small and our population is normally distributed and our population standard deviation is known, we're still going to use x bar plus or minus z times the standard error. But if our sample sizes are small for a normally distributed population with unknown population standard deviation, we'll revert to using the t distribution. If our population is not normally distributed and our sample sizes are large, given that our population standard deviation is known, we can still use the z distribution to construct our confidence interval. However, if our sample population standard deviation is not known, we shall revert to using the t distribution, given that our sample sizes are large. If our population is not normally distributed and our sample sizes are small, that is less than 30, then we cannot use the normal distribution approach, but we may look at other non-parametric procedures to estimate our confidence interval, which is actually beyond the scope of this study. Let's take another example that you could also try your hands on. According to the USA Today, customers are not settling for automobiles straight off the production lines. As an example, those who purchase a $335,000 Rolls-Royce typically add $25,000 in accessories. One of the affordable automobiles to receive additions is the BMW's Mini Cooper. A sample of 179 Mini purchases yielded a sample mean of $5,000 above the $20,200 base sticker price. Suppose that the cost of accessories purchased for all Mini Coopers has a standard deviation of 1,500. Calculate a 95% confidence interval for the average cost of accessories on Mini Coopers. Determine the margin of error in estimating the average cost of accessories on the Mini Coopers, and estimate the sample size that will be required to reduce the margin of error by 50%. I hope you'll be able to try your hands on this. Let's go on to estimating confidence interval for a proportion. Just as we did for the mean, an estimate for the population proportion can also be calculated by adding an allowance for uncertainty to the sample proportion. We recall that the sample proportion is also approximately normal if the sample size is large and it has a standard deviation of sigma being equal to p times 1 minus p all over n. And if the population standard deviation is unknown, we are going to use the sample estimate, which is p bar times 1 minus p bar over n, all under the square root sign. Therefore, in calculating the upper and lower confidence limit for a population proportion, we are going to have p bar plus or minus z alpha over 2 multiplying our standard error. And in this case, our standard error is giving us p bar times 1 minus p bar divided by n, all under the square root sign. Z is the standard normal value for the confidence level desired. P is the sample proportion, and n is the sample size. We take an example. A random sample of size 100 shows that 25 are left-handed. Form a 95% confidence interval for the true population of left-handers. So we have our p bar, which is giving us 25 over 100, which is 0.25. Then our standard error, which is p bar times 1 minus p bar divided by n square root, is giving us 0.25 times 0.75 divided by the sample size, which is 100. Now this gives us 0.433, and therefore we have our confidence interval for the proportion being 0.25 plus or minus 1.96 being our critical value times 0.0433, and it gives us a lower bound of 0.1651 and an upper bound of 0.3349. That is, we are 95% confident that the true percentage of left-handed in the population is between 16.51%, given by the value of 0.1651, and 33.49%. We also believe that if there are increases or changes in the sample size, it would affect the width of the confidence interval. For instance, if there are increases in the sample size, it will reduce the width of the confidence interval. Similarly, if the sample size decreases, we are going to increase the width of the confidence interval. For example, if the sample size in the previous example is doubled to 200, and if 50 people are left-handed in a sample, then our interval will be centered at 0.25, but the width will shrink to a lower bound of 0.19, and an upper bound of 0.31. We can also find the margin of error as well as the required sample size for proportion-related problems. So this is giving us the margin of error, and this formula is giving us the required sample size that is needed. We take an example. How large should a sample be in order to estimate the true proportion of defective items in a large population with a margin of error of 3% with 95% confidence? Assume that a pilot sample yields p equals to 0.12. So, for 95% confidence interval, we set our z to be 1.96. Our margin of error is giving us 3%, that is 0.03. Our p is 0.12, and therefore we use this to estimate our value of n, which is z squared, that is 1.96 squared, multiplying p times 1 minus p, that is 0.12, times 1 minus 0.12, which gives us actually 0.88, divided by 0.03 squared. And that gives us a sample of size 450.74, approximated to 451. That tells us that in order to get what we need, a 95% confidence that our population will be within a margin of 3%, we need a sample of size 451. This brings us to the end of session 8. Thank you very much.